Thank you. Can you hear me well?
Yes, we can hear you.
Excellent. Well, thanks everybody for coming and staying that late. I don't know if there's a mechanism to ask questions. Sergej, is there a mechanism if somebody needs to interject or not?
Yeah, there are mics here, and so they will just ask you, and you will
Okay,
hear.
excellent. Then, yeah, everybody please feel free to interject so that I'm not talking to myself. So today's I'm gonna explain about some interesting symmetry realizations at finite temperature that we call entropic order. It's based off quite a bit of work that I and others have been involved in over the last couple of years, but especially last year, 2025. There is this paper that will be one of the main things I'll explain today, and even more so the very last paper from December with Xiaoyang Wang, Andy Lucas, who are from Colorado, and Fyodor Popov and Tin Suleiman Pasic. Fyodor Popov is a postdoc at the Simon Center, and Tin Suleiman Pasic is a professor in the UK in Durham. So this will be the main focus points, but there is some previous work that I'll also mention. So I'll first review some simple, generally accepted principles in thermal physics, and I'll explain the connection to black holes. Actually, that was my original motivation to work on this problem, so I'll just mention it. And then I'll explain the minimal model that we found that we call the AIM model, or the arithmetic Ising model. And then if I have time, I'll go to slightly more complicated topics like the quantum field theory models and various other generalizations. So I'll start with just very simple introduction. Of course, we know that in many systems at zero temperature, order appears spontaneously. So for instance, in ice, you get spontaneous order due to the breakdown of translational symmetry. So you can get nice crystals. Other examples that appear in nature other than solids are ferromagnets, chiral symmetry breaking in QCD, antiferromagnets, superfluids, superconductors. These are all examples of order that appears at low temperatures. Now, we believe that pretty much in any such example, as we heat up the system, the order must disappear. And this is just some kind of high school intuition that when the system is at high temperature, the kinetic energy is so large that all the possible orderly arrangements are broken down, or something along those lines. That's the intuition. For instance, if you take a ferromagnet with all the nuclei spins pointing in the same direction, once you heat it up, they get completely disordered. Okay, this is some usual intuition, and formally we have this thermal density matrix, or the thermal Gibbs ensemble if you're in classical physics, and we say that all the symmetries are restored for a sufficiently small beta. Also, if you're interested in topological order or various other kinds of order, the intuition is the same. That at small enough beta, any such order would disappear. And of course, we see that in experiments. So this is an example of some typical magnet that at low temperature has a ferromagnetic phase. That's the green phase, while the yellow phase is a disordered phase. And you see that at low temperatures, you can tune some external parameters, such as magnetic fields, to go between one and the other. But when you heat the temperature, when you crank up the temperature above this Tc, you don't have the ferromagnetic phase anymore. So order is not compatible with high temperature. Now, there is a question of, is it really a law of nature that any type of order must disappear at high temperatures? So is it a law of nature? So why is it happening? So usually we would say that at finite temperature, instead of minimizing just the energy, we minimize the energy minus the degeneracy of states. So formally E minus ST, where S is the entropy. And so at high temperatures, we must maximize the entropy. And entropy pretty much by definition is a measure of disorder. So you would say that from this, we learn that at high temperature, disorder must dominate and there cannot be any order. I'll show you today that this intuition is false, that high entropy does not imply disorder. But that's what we're usually told, that disorder is equal to high entropy. Okay, if there are any questions, please stop me. I might also stop by myself every couple of minutes, asking if there are questions. Now, there is an interesting interpretation of this story also for anti-de Sitter space. So, for holographic systems, there is a dual description of this thermal density matrix in terms of a black hole in ADS. And black holes in ADS have some interesting properties that mirror the fact that at high temperatures we should not have order. So, let me just remind you of that. It is believed in the community that large ADS black holes, there is no hair. For large non-spinning, non-charged ADS black holes, which are dual to this thermal ensemble, e to the minus beta h, it's widely believed that there is no hair. Oh, by the way, my video is off. I cannot turn it on. It says that the host disabled it. Is this a problem or should I keep going?
I think
it says that it's disabled by the host. Okay. So for large ADS black holes, there are many indications in the literature that at least for large enough ADS black holes that are not spinning and not charged, it's widely believed that there is no hair. And interestingly, hair is just dual to symmetry breaking. So in some sense, the no hair theorem, if you wanted to prove it, is the same as proving that quantum systems at high temperatures cannot break any symmetries or cannot have order. And that's originally why I started thinking about this question. Now, a more precise statement is that, for instance, Alex Bushell from Perimeter Institute and Waterloo University, I guess, Alex Bushell has found many large black holes with hair within supergravity theory. But as far as I know, if you look at UV complete stringy models, none of them has hair. The UV complete stringy models, the large black holes within those models do not have hair. So there might be some interesting statement here that at least UV complete quantum gravity theories are such that large black holes have no hair. But at least in supergravity, there are counterexamples. Anyway, resolving this question is why I originally started working on it, but by now it's a bit, at the end, I'm not sure what the answer is to this no hair question, but it's formally dual to the question of order at high temperatures. Okay. Now, under some rigorous assumptions, there are rigorous theorems that actually prove that at high enough temperatures, this ensemble, the Gibbs ensemble, is trivial. So you can, yes?
Question about the hair. So by hair, you mean that there are no other things except mass, electric charge, and angular momentum?
Mm-hmm. Yeah.
And why presence of hair relates to symmetry breaking?
Okay, excellent. So by hair, what you practically mean is that there is some kind of fuzz or there is some condensate near the black hole horizon. So the black hole horizon usually is characterized, as you said, just by mass. And if it's not charged or not spinning, that's it. It's just mass. So hair manifests itself around black holes by some kind of fuzz or a condensate near the black hole. So in the constructions of Bushell, for instance, the hairy black holes have some scalar condensate. And when you have a scalar condensate inside the hologram, here in the ADS dual, that manifests as an expectation value for an order parameter on the boundary. So hair around the black hole is dual to expectation values of various fields in the thermal ensemble. So it's closely related to the question of symmetry breaking at high temperatures. Is that okay? Okay. Let me just now review some work that mathematicians have done like a half a century ago, and also more recently in the quantum context, which essentially proves that at high enough temperatures there cannot be order. Oh, I was able to turn on the video miraculously. So that essentially proves that there is no order at high enough temperatures. So this can be proven rigorously with various assumptions, and I recommend you this book if you want to learn about it, by Barry Simon. So in the Russian community, these theorems are called the Brushin theorems, and in the West it's called the uniqueness of the Gibbs state. And last year, people even proved the quantum version of the same statement, which is called the heat death of entanglement in this group. So what are these statements saying? Well, they basically say that there is no order and no correlations at high temperatures. And precisely they say that there is always a critical beta. And if you go to temperatures which are even higher than that, correlation functions factorize up to exponentially small corrections. That's a classical statistical mechanics theorem. And if correlation functions factorize, then cannot be order, because 1-point functions vanish at any finite but large volume. So therefore 2-point functions also have to vanish at large separations up to exponentially small corrections, and that's it. So people have basically proven that at high temperatures there is no order under some assumptions. And there is a quantum version of the same statement, which is interesting, where it's shown that there is always a critical temperature and above which the density matrix becomes separable. A separable density matrix means that it's essentially a sum of classical density matrices, so they're factorized. And that also means that entanglement dies, and like all the quantum spookiness ceases to exist at high temperatures. So these are rigorous theorems that can be proven about high temperature physics under various assumptions. And of course, the devil is in those assumptions. So now I'll tell you what are the main assumptions of these theorems. In both cases, the quantum and the classical case, there is a crucial assumption, which is that the uniform distribution over the space of states exists. Another crucial assumption is that the space of states is a tensor product. So let me just make some obvious comments about these two assumptions. First of all, in quantum field theory, if you don't care about condensed matter or statistical mechanics and you just want to do quantum field theory, in quantum field theory, the space of states is certainly not a direct product and the uniform distribution doesn't exist. Let me just explain what it means. So you can put a uniform distribution on the interval, so you can draw a number from 0 to 1 with uniform distribution. But there is no such thing as drawing a number from the integers with uniform distribution. There is no uniform distribution over the integers. There is the uniform distribution maybe over the numbers 1, 2, 3, or the numbers from 0 to 1. But there is no uniform distribution over the integers. So the first assumption is like saying that there are not that many states. And the second assumption is about the direct product structure of the space of states. Now in QFT, of course, there is too many states for 1 to make sense, and also for 2 to make sense. But also in lattice systems, such as in Hubbard models, 1 is violated, and in gauge theories on the lattice 2 is violated. So there's still a lot of room to look for interesting models. Despite of this, the Brushin or uniqueness theorems for the Gibbs states. And that's what we're gonna do today. I'll show you that there are some extremely simple models that look very physical, that avoid these theorems, and have very interesting phase diagrams at high temperatures. Are there any questions about the Brushin theorem or those assumptions? Okay. So I'll just summarize what I said so far. Common sense experiments and the no-hair theorem all suggest that order must vanish at sufficiently high temperatures. And we know it from daily experience. Magnets fall from the fridge if you go to high temperature. But today we'll explore whether it's actually a true fact also about quantum field theory and about some lattice models.
Can I ask a question?
Sure.
So the Dobrushin theorem that you mentioned, the quantum version does not imply that there's no order, right? Because you can have a separable state which is still ordered, classically ordered. So
Yes. Yes, you're 100% right. This formula on its own does not imply that there is no order, because there could be classical order. But this property comes on top of this property. So you can also establish this. About quantum models, you can establish both results. That the whole density matrix is classical, but also classical correlations go to 0. So both are true. Now, this is interesting because it implies that there is no entanglement. You know, like people are desperately interested in topological order surviving to high temperature. But this kind of kills entanglement, and this kills classical correlations. Is that okay?
Yeah, thanks.
Now, as I said, mathematically speaking, both are not true because of these assumptions. You can find counterexamples, and I'll show you some today. Whether somebody can take one of the counterexamples I'll show you today and build a quantum computer or a magnet that never loses its magnetism, we will have to wait and see. But I think the models look somewhat realistic. Okay? Okay. So as I said, in quantum field theory, it's always violated. It's also violated in some lattice models. I mean, not the consequences of the theorem. It's still true that most quantum field theories probably don't have order at high temperatures, but the assumptions are violated. So today I want to address 3 questions. Is it actually correct that large entropy means lack of order? I'll show you that the answer is no. Second question is, are there local lattice models which are ordered at high temperature? I'll show you that the answer is yes. And lastly, are there also examples in quantum field theory of order at high temperatures? And for that also, I will show you that the answer is yes. Well, that's just saying that using the examples from today, you could cook up materials which have this bizarre kind of phase diagram that order dominates at any temperature, and it's the disordered phase that is only appearing at low temperatures, but most of the phase diagram is filled with an ordered state, which is a very bizarre thing, but they exist. This is a technical comment. Okay, so first I'll start from classical StatMech in 2 dimensions. It's the cleanest setup, no confusions. Everything can be put on the computer. So we're gonna cook up a Hamiltonian, which depends on some configuration space, and calculate the Gibbs partition function, and the Boltzmann weights and the partition function, and then we'll study the microstates. Okay, so here is the main model that I wanted to show you first. It's the main model which shows that high entropy is not equal to disorder. So you can have order and high entropy at the same time. So we start from an L by L rectangular lattice, just square lattice. And at each plaquette, you can put a non-negative integer. 0, 1, 2. What does this integer represent? It represents, let's say, how many bosons live on this plaquette. It's some kind of classical Hubbard model, if you want. So in each plaquette, we put a non-negative integer, and the energy functional is the following. So first of all, there is a linear term, which means every time you put some particle, you pay some constant energy, n. By the way, this number n, maybe you could think about it as the number of bosons, but you could also think about it as the occupation number of some Rydberg atom. Maybe it's the internal level of some atom. Okay, so you have some linear term which says that like going to very high integers costs you some linear energy. But then most importantly, there is a repulsion, but it's not the same repulsion term that you might have seen in the Hubbard model. This repulsion is across for neighbors. So if there are 3 particles in this plaquette and 5 particles in this plaquette, you multiply 3 by 5 and you pay 15 units of energy penalty. So this symbol means that these are nearest neighbors. So if you put a particle here, it repels particles in 4 sites which are nearby, which share a common edge, which are the nearest neighbors. And okay, and that's it. Okay, so this is the model. It's like an Ising model type thing. It's very similar to the Ising model. Some nearest neighbor interaction, some penalty that looks like a constant magnetic field in the Ising language. And we're gonna just use this model and analyze it. Okay, is the model clear, or anybody has any remarks or questions about it? It's crucial to understand the model at least, because I'm gonna spend a few slides now showing you what it does, which is very extraordinary. Okay, so the model is simple enough. As I said, we don't know how to interpret.
Wait,
Yes.
wait, there is a question. Just give us.
The question, is it important that bosons live on plaquettes and not on sites? Oh,
No, it's absolutely irrelevant. You can put, in fact, in the paper, they live on sites. It's just that when I drew these arrows, it was easier for me to have the arrows hit the plaquette. So I decided to put the bosons on plaquettes. It's insignificant. Okay. This model has a parameter, I forgot to say, U. So when I said 15 units of energy, I meant 15 U. U is the parameter which you can tune about saying how much they repel. Of course, U equals 0, the model is solvable because the sites don't talk to each other. And each site will just have some Poisson distribution of particles, and that's it. Okay, so this model has not yet been realized experimentally. I believe some people might try in the future. So maybe this N will be realized as an internal level of some atom. Maybe this would be a more natural realization. And anyway, we call this the arithmetic Ising model because it has no negative integers and it's very similar to Ising. Okay, so here is the result of simulations, and then I'll explain what the hell is going on. How is it possible?
I have a question. Can I ask?
Sure.
Hi, Zohar. This is Spencer. Hi.
Oh, hi, Spenda.
There is no bound on these integers, right? I mean, suppose I have a large integer to bound these numbers. Will that make a difference to this model?
It's an excellent question. I'll answer this question when I explain the phase diagram of the model where the integer is unbounded, and then I'll say how it changes when the integer is bounded.
Okay.
Okay?
Thanks.
It will be easier that way. Okay. So let's first analyze. First of all, the model with the unbounded integer is completely well defined. You can prove mathematically that the partition function exists. So let's analyze what it does. So it has this bizarre property that, okay, so first of all, if mu is 1, by the way, I put the chemical potential to 1 by no loss of generality. So mu is 1, so the horizontal axis is just capital U. So one thing that this model exhibits numerically is that if U is smaller than a half, it always is in a disordered phase. Now this is a screenshot. Sorry. This is a screenshot of a disordered phase. What is a disordered phase? We have a lattice. Some plaquettes have particles. Some plaquettes don't have that many particles, and it's color coded. So very hot colors mean many particles. Very cold colors mean not that many particles. Okay? So this is a phase that you can call gas or liquid. It's just completely disordered, and there's some clamps that are moving, some clamps that appear in a disorderly fashion. So this is like a completely disordered phase. And if U is smaller than a half, This is the phase that appears at any temperature. But if U is bigger than a half, we believe this black line asymptotes to half. We spent probably a half a year trying to prove it mathematically, that a half is a critical point of this model. We try to prove that this black line asymptotes to a half. We now have maybe the beginning of an argument, but not a proof. Anyway, it's still an open question, but we see it numerically. And so the statement is that for every U that is bigger than a half, there is a high enough temperature from which the model becomes a solid. So it's a bizarre solid. Usually solids melt when you heat them up. This solid appears at some high temperature and then never disappears. You cannot melt this solid. So what do you see if you take a snapshot? You see this very nice checkerboard pattern, where again, very hot colors represent many particles and very cold colors represent few particles. So you see that the particles occupy one sublattice. So it's like spontaneous symmetry breaking. The translational symmetry of the lattice is spontaneously broken to from Z to 2Z. So there is some Z2 that is spontaneously broken. And you just choose a checkerboard spontaneously. That's why we call it a solid state. Now, I'll explain soon how come that the solid has more entropy than a gas. Usually gas has more entropy than solid because the solid is ordered and you lose entropy by this nice checkerboard pattern. Okay, anyway, that's the statement, that this model has a solid state up to infinite temperature, like strictly speaking up to infinite temperature, and it happens for any U that is bigger than a half. Now, to Spenta's question, if I were to limit the number of the allowed integers up to some capital N, this would be capped. So the solid would exist up to temperatures of order capital N, and then it would go back to the gas. And I mean, if this model is ever realized experimentally, this little n will be capped, of course, but it still leads to a new mechanism for very high temperature transitions. Because if we could cap in experiment this little n, let's say by 10, it would mean that the solid survives up to 10 U, up to temperatures of order like 10 U, and U is the fundamental scale in the problem. So it would mean that you were able to push the transition temperature of an ordered state much above the fundamental scale of the problem, and it's still useful. Like in practice for superconductors at high temperatures or topological order, etc. So once you cap this little n, the solid does not exist at infinite temperature, but it exists only up to temperatures of order capital N. Okay, so that's the answer. And of course, if you cap the little n, you're within the Brownian's theorem because the unit distribution exists and it's a direct product space. So that's why it happens. Okay, if there are no questions about this phase diagram, this we can prove analytically, that if the temperature is smaller than 4.27, it's always in a gas phase. So the solid phase begins from that. This number we can basically calculate analytically. But the half is much more complicated, it turned out. Yeah.
It seems intuitively that these entropic arguments hold for any hypercubic lattice in any dimension. Do you confirm that it is the case, or is D equals 2 crucial for the shape of this phase diagram?
No, I think it's a good question. I think it will hold in pretty much any dimension above 2. In one dimension, it cannot work because of the parallels arguments about fluctuations in 1D. You cannot break symmetries in 1D. But I think 2 and above should work, yeah. Now, before I go to the equations, I want to explain intuitively, how is it possible that the solid doesn't melt? So solid usually has smaller entropy than gas because, if you look at a snapshot of this microstate in some small region, you can easily reconstruct the microstate everywhere else. It has very low entropy, right? Because you know that only one checkerboard, only one sublattice is filled with particles. So that automatically reduces the entropy by like a half to the power n, yeah? Because it's like, it looks the same everywhere. So it has no information. Like if you start submitting, in the language of information theory, if you start submitting the data about the state to somebody, sending it via telephone, you don't have to keep saying, oh, this sublattice is empty, this sublattice is full, because it's obvious, it becomes obvious. So in that sense, this state has low entropy. But what saves the day is that the hot sites are quite hot. So the sublattice that is full is actually full with a lot of particles. So if you try to submit, to send to somebody by telephone the data about the state, you'll have to say, oh, this hot plaquette has 5,736 particles, and this one has 5,854, etc., etc. So there is actually a lot of entropy hiding in the sublattice that is occupied, because it's occupied with a lot of particles. I'll show you the equations soon. On the other hand, in a gas, there is no order, so no sublattice is preferred, but the number of hot sites is smaller. So if you try to put them side by side at the same temperature, let's say I try to put a snapshot of a gas phase here, which is not a good state, it's metastable maybe. It's not a stable state, but still, what you would find is that yes, you lost some entropy because of the checkerboard, but the hot sites are more hot than the hot sites in the gas. And you end up having to spend a lot of time sending this information by telephone, yeah? So there is a lot of entropy from the hot sites, even though you lose some entropy from the solid state structure. That's the underlying physics here. That it looks like it's a low entropy state, but it's a high entropy state, and that's why it never melts. Now let me show you the equations that justify all these words. So this is mean field theory calculations. It's not the actual model. Mean field theory is not correct here, but mean field theory gives you some qualitative understanding. So let's consider the gas phase. In mean field theory, if you do some calculations, you'll find that the average number of particles goes like the square root of temperature in the gas phase, and you can estimate the partition function like that. By contrast, let's consider the checkerboard phase, which is a solid phase. If we assume that one sublattice is full and the other is completely empty, we will find that the number of particles on the full sublattice, on the occupied sublattice, is proportional to temperature. And that's the key point. In the gas phase, the number of particles is proportional to square root of temperature. And in this model, in the gas phase, it's proportional to square root of temperature. And in the checkerboard phase, it's proportional to temperature. And that's where the entropy is hiding. Then you can calculate the partition function, you can compare the free energies, and you'll find, roughly speaking, this kind of diagram, even within mean field theory. I'll show you some diagrams soon comparing actual simulations to mean field theory, and you'll see that mean field theory is within 10% of the correct answer. Now, mean field theory becomes exact in some limit, which we call the colored arithmetic Ising model. So the idea in this model is that maybe an integer, a non-negative integer, is made out of k-independent non-negative integers on every plaquette. It's kind of the very standard large species limit, or large n limit, large k limit here, that we use in QFT and condensed matter. And it turns out that if you just assume that every non-negative integer is the sum of k-independent non-negative integers, you can show that the model becomes solvable, and you can do a systematic 1 by k expansion. And we spent a lot of time analyzing it, and it's a very good approximation to the model with k equals 1, where mean field theory is incorrect. But in this model, at infinite k, mean field theory becomes exact, and you can do perturbation theory in 1 by k. There are some interesting logarithms, some interesting RG type equations. It's kind of a very rich story, but I'm not going to explain it. It just shows that everything holds together. So that's an example of what you see in numerical simulations at k equals 1, so the original model. Here we vary u, this coupling constant, and I told you that around a half, a solid appears. So you can see it very nicely. We crank up u, and it solidifies at 1000 degrees. Here you can see the mean field theory. This O is the order parameter for the checkerboard phase. So we calculate the expectation value of the checkerboard of the order parameter. So what is this order parameter? It's the number of sites on lattice on sublattice A minus the number of particles on sublattice A minus the number of particles on sublattice B normalized by the number of sites. So this is the answer with mean field theory. It's again at 1000 degrees. You see that at a half, mean field theory predicts that order develops. Now in real life, as you vary the system size, you get this kind of graphs. And we think numerically it's going to a half, but as I said, it's an open question. We were not able to prove that it really asymptotes to a half. It seems so numerically. Okay, so the mechanism in this model is very clear. The system prefers to sacrifice an order parameter, so it orders and becomes a solid because it gains a lot of entropy from some other place. And that's the mechanism. That mechanism can be used for anything. Okay, so I'll show you a few more examples today. I'll show you a ferromagnetic example, not a solid, a ferromagnet that lives at infinite temperature. But you can use it for superconductors. You can easily cook up models where forming a Cooper pair is entropically beneficial and the Cooper pair just never disappears. You can use it for topological order. And the idea is always the same. You cook up a model where an ordered state has a higher entropy because of some hidden variable in quotation marks. Is the idea clear? Now I'm going to go to quantum field theory to show you that the same phenomenon can happen in very simple vector models in 3 dimensions, 2 plus 1. Any questions about what I said so far? Okay. Now I'll show you the very familiar setup for quantum field theories, which is the ON model. The ON model itself, which is just a field theory in 2 plus 1 dimensions for a degree of freedom, which is a vector in n dimensions, does not have order at infinite temperature. In fact, like 35 years ago or so, Subir Sajdev and various other people computed the correlation function, and it's decaying exponentially. Okay, so they calculated this 2-point function, and they found that it decays exponentially with this exact answer in the infinite n limit. So we know that the ordinary magnet does not ferromagnetize at high temperatures. Okay, that's why magnets fall off the fridge at high temperatures, and there is a Curie temperature. Today I'll show you a variant of that model. It's not the ordinary ON magnet. I'll show you a magnet that in condensed matter is called the biconical magnet that shockingly does magnetize at infinite temperature. So what is the construction? You start from the ON model and you add another degree of freedom, which you call psi, and it couples to the order, so it has a kinetic term in Landau-Ginzburg. It's just a Landau-Ginzburg description for a magnet that's called the biconical magnet. So you start from the ON magnet, you add another degree of freedom psi, you add the kinetic term, and then you add the coupling between the phi squared order parameter of the ON model and psi squared, where psi is this new degree of freedom. And it turns out that this coupling is relevant. So there is some renormalization group flow to some possibly new fixed point. How do we know that this coupling is relevant? We know the scaling dimension of this composite operator phi, and therefore we can calculate at very small lambda the beta function for lambda. And using the result of Itzigson-Zuber for the scaling dimension of this composite, we can find that it's indeed slightly relevant. So I'll show you the diagrams. Basically, the work is to calculate the beta function for this lambda. There are like 10 diagrams, if I'm counting roughly correctly. There is another coupling constant G, which is like a sextic interaction of this new degree of freedom with itself. So you have to calculate 2 beta functions. We can do these calculations in the large n limit, where n is the number of components for this phi, and it boils down to these 10 or 15 diagrams. It took a lot of time to calculate them, and I wasn't able to do it on my own because of one diagram that confused me forever, which is this one. But Fyodor Popov was able to analyze it correctly. And now we have the result, hopefully. And the bottom line is the following. The bottom line is that this is the beta function for lambda. It has a new interesting fixed point, and it agrees with what condensed matter people call the biconical magnet. So it's just a vector model in 2 + 1 dimensions with ON times Z2 symmetry. And magnets with such symmetry are known for many years. So we think we found this magnet in perturbation theory in 1/n using this RG flow from the ON model coupled to psi. Okay, now the next exercise you must do is that you must put this model at finite temperature to try to understand what does it do at finite temperature. And the idea is very clear. What we want to see is that this will behave similarly to this arithmetic Ising model. So I'm going to argue that what this model does is that it makes psi condense at any temperature, because that opens up a lot of fluctuations for phi, and it becomes entropically favorable. So the model will break the Z2 ferromagnetic symmetry spontaneously at any temperature, because that actually increases the entropy in the phi fields. So that's what it's going to do. And indeed, you can do large n calculations in this model, and you find that the 1-point function of the psi field, it goes like the square root of temperature at large n with a non-zero coefficient. And it has this very interesting phase diagram. It's a conformal field theory with some fixed point that I showed to you. At 0 temperature, as you heat up the system, it always stays a ferromagnet. And we believe the mechanism is the same as in the AIM model, namely, this is entropically favored because it opens up a large phase space of fluctuations for the phi order parameter. And okay, these calculations are in the infinite n limit. So you see there is 1/n. So the question is, what is the exact statement? Recently, there was a paper by Hawashin, Rong, and Scherer doing numerical simulations on the computer. And they argue that this will happen as long as the number of components in the phi field is 10 or above. We did some calculations in the 1/n expansion, extrapolate them to small n, which of course is maybe illegal, but that's the best you can do now. And we think that maybe even n equals 4 or 5 will do the job. So at least this quantum field theory at finite n certainly exhibits order at infinite temperature. Okay, that's the first example I think that's known to humanity of this kind of thing. It's a consistent QFT, it's unitary, it has bounded energy from below, it's local interactions, and we think that at any temperature it is a ferromagnet. Okay, so this is the claim, and the claim is that it's not only that it's true at infinite n, it's actually true at finite n. And these diagrams prove it, because we just did subleading the first non-trivial 1/n corrections. That's how this conclusion is achieved. Okay. Are there any questions about the QFT story? Okay. So I'll just make 2 minutes, like just to close. I'll show you that you can do the same with Cooper pairs. I won't explain the details. It's in the paper. The idea with superconductivity is the same. You take the usual BCS order parameter, which is the condensate of Cooper pairs, and you couple it to this order parameter, which is the ON phi field. And it's very similar calculations. You just do some gap equations, and you find that the phase diagram of this model is that it's a superconductor up to the cutoff. So basically at any temperature. The Cooper pairs just don't want to disappear. In the usual BCS story, Cooper pairs disappear at very low temperatures, which is exponentially small. Well, the exponential factor is the density is determined by the interaction strengths and the density of states. And in our model, because of this mechanism, you get entropic order at any temperature. So I won't go into the details of that. I'll just summarize with some open questions. So I showed you a general mechanism that shows that typical excited states of some consistent quantum and classical systems can be ordered. They carry the highest entropy. I showed that for solids, ferromagnets, and I mentioned also superconductors, you can do it for topological order as well. And there are many obvious open questions. Can any of this be realized in real life? We don't see such phenomena in real life, but they seem to be not particularly fine-tuned in the models that I showed you. There are lots of technical questions about the arithmetic Ising model, about this phase diagram. Can you prove it? Is it second order everywhere between the gas and the liquid, between the liquid and the solid, etc.? Now, all the examples today were in 2+1 dimensions. You can ask, what about 3+1 dimensions? What about gauge theories? I haven't discussed gauge theories. All the examples today were either scalar theories or just Ising type models. And I mean, the last question is related to the first question. What is special about this biconical QFT? It doesn't, so this phenomenon doesn't happen in the ON model, but is it generic? Or is it something special that happens in very special magnets? So I don't know how generic it is. It seems to me that it's pretty generic, but this is to understand in the future. Okay, this is the end. Thank you. If there are any questions, I can take them. Thank you.
Yeah.
I have one question, Zohar.
Go ahead.
Yes.
Yeah. So if you look at that ON model with this additional psi field added, so that if the psi field is not there, this model is asymptotically free. It's some massive number of particles, right? Now, if you add this new field, does this model have ultraviolet completeness? Is this well defined at short distances, or?
Yeah, it's an asymptotically free model because in 2+1 dimensions, this is a super normalizable interaction.
Okay.
Yeah, it's as good as anything you can imagine. It's asymptotically free, it's local, it's unitary, it flows to a fixed point.
Okay.
And then at finite temperature, it has order at any temperature.
Yeah. Okay. Thank you.
More questions. Please take the mic.
In model, the entropic order, of course, it's a separable state, right? Like it still satisfies the second quantum condition because it's a classical model.
You're asking if this model, the density matrix, is still separable and the order is classical.
Yeah, and the second question is like, can you realize some entangled order at high temperature?
Okay, for the first question, the honest answer is I'm not sure. We didn't calculate it. We just calculated the classical order, like expectation value of the order parameter. I believe you are correct. Okay, 99%, I would say, yes, the density matrix in this particular model is still separable. Now, you're asking if we can cook up models where the density matrix is not separable at very high temperatures.
Mm-hmm.
On the lattice, yes. On the lattice, we wrote down some models which look like that, with some gauge fields on the lattice that do have topological entanglement entropy at any temperature. In quantum field theory, I haven't tried this idea. I haven't thought about it, so it's a good question. If there is some topological order at very high temperatures in QFT. It's a good question. I never thought about it. Okay?
Thanks.
Yeah,
I don't believe that there will be an obstruction, but it will be nice to see.
I'm wondering about the dynamical properties of those high temperature broken symmetry states. For example, would you have Goldstone modes in the case where it's a continuous symmetry that's broken at high temperature? Would you have the same Meissner effect if it's a superconductor? Does it change the phenomenology the fact that it's entropy that stabilizes the order.
Okay, good. So about the Goldstone modes, yes, Goldstone's theorem is still true. So these models at high temperature, they don't have a gap. They don't have the bias screening. They still they have Goldstone modes, so they're gapless even at very high temperature. So that's yes. And about the superconductors, yes, I think they continue to obey the Meissner effect at high temperatures. Yes. So the Meissner effect will continue up to infinite temperatures.
Yeah.
Of course, in quotation marks. No, nobody really thinks that at infinite temperature you can get a superconductor. But on a piece of paper, you can write down these kind of models that appear to be superconducting up to the cutoff. So yes, these models on a piece of paper will obey the Meissner effect at very high temperatures.
Next question.
The QFT model that you described was ON, and then you coupled it with like a secondary order parameter, right?
Yes.
So this type of models have been studied in solid states, like since Landau in the Russian school of doing solid state. Are you sure that there are not materials that show this behavior? Have you checked?
Well, no, I think there is. I think that this particular construction here, which is Landau-Ginzburg, as you said, realizes what is in condensed matter called the biconical magnet.
So this type of materials with high temperature order should exist, right?
I believe so. I will say something even more. I believe it's extremely similar to a material that I made a slide about it, but I just jumped over this slide. There is a certain salt that's called the Rochelle salt, which people always in condensed matter believe is very similar to the biconical magnet, that it's kind of a very similar effective theory. And so indeed the Rochelle salt has very strange phase diagram with some high temperature order. So I think essentially the answer must be yes, but I can't say for sure. Like I don't know exactly which magnet is in this universality class. And so
would you be able to realize them in a similar fashion with dislocations or like gaps in solids?
I didn't think about it.
Vacancies or something like that?
You want to realize this model like in the lab? That's what you're saying?
Yeah, why not?
Well, of course, that's my dream too, that some of this will be shown to exist in real life, yeah?
But at the end, sorry, like a very basic question. All what you want is the high temperature phase to have higher, to be more ordered than the lower one. To have
but that's not a trivial thing to achieve. Like this, people believe at least that this cannot happen. I think we just showed counterexamples.
Sure, okay, I do know, but I think there are books from like 70s, 80s with thousands of classified Landau transitions. I don't know, I haven't checked all of them, but there should be something there, right?
My personal opinion is that even for this vector model, the finite temperature calculations that we did in 2+1 dimensions are new. And in fact, I can show you that I tried to do them in 2020 with these collaborators and we didn't succeed. We did only epsilon expansion at the end. And only in 2025, Fyodor found how to do it because of this one diagram that we didn't know how to calculate in the large n limit. So yeah, you're right that there is a huge amount of literature on models of this type. I agree. But I believe that the thermal phase diagram that I showed you today is new.
Okay.
I don't think anybody knew that this model has finite temperature order.
So I have also question about this model. So I got your intuition for this arithmetic Ising model, why the solid is preferred at high temperature. So could you repeat why you kind of coupling to this extra field increases entropy of the high temperature state.
Oh, it's about the QFT model. You want me to try to explain why it works?
Right.
Yeah, so let's go back to the calculation of the just standard ON model, which you can also find in, I think, in Sajdev's book. So what happens in this model is that you crank up the temperature and you get the thermal mass. And what happens is that the field phi goes to the origin. So there is no symmetry breaking in this model at high temperatures because you get a positive thermal mass squared. And as you crank up the mass, the field goes closer and closer to the origin, and correlations go to zero, exponentially like that. Okay, now, what does this model do? What this does is, because of this minus sign, there is a crucial minus sign. So the fixed point, there is a unitary fixed point where lambda is positive, you see? So at the fixed point, this coupling constant goes to -1 at the fixed point in some conventions. It looks like it's not bounded from below. You might worry about it, but it's actually completely bounded from below because there is also a sextic interaction with a positive fixed point value. So it's okay. But it's crucial that the sign here is negative, and then there is a positive sextic interaction, which stabilizes the whole model. So the model is well defined and unitary. But what it says is that because of this minus sign, if psi obtains a vev, it kind of gives phi squared a negative mass squared, you see? And this makes the thermal mass squared of phi a little bit smaller than what Subhro computed. So Subhro computed that the thermal mass squared of phi is this squared, but in this model, because of the ferromagnetic order, it's a little bit smaller. And because the mass squared of phi is a little bit smaller than in Subhro's model, phi can fluctuate more wildly, more actively, more exuberantly, because it kind of lowers the thermal mass squared. So that's the crucial thing.
So this explains why you get a VEF for psi.
Yes. So this very
you get more from that.
Yeah, so this alone suggests that psi will want to get a VEV, because entropically this would increase the entropy in the phi fields. And that's also why there seems to be a bound on how many phi fields you got, maybe 10, maybe 5, because you want this increase in entropy to overcompensate over the loss of entropy from having a ferromagnetic order. Because you lose a lot of entropy by going to a ferromagnetic phase, and you want the phi fields to compensate for that. And that's why you need a few of them, maybe 10, maybe 5.
Right. And the claim is that this VEF goes to up to infinite temperature. Is it right? Or for this?
The VEV is like this. We calculated the VEV. This is the VEV at high temperatures.
I see.
At least at large enough n, like at n equals 100, this is the correct answer.
Good. Thank you. So, more questions? Any more questions? Yeah, please.
I'm trying to understand how essential the symmetry is. So, for example, let's consider the first AIM model, and that model had Z symmetry. And in the order phase, it was broken to Z2. So if I add some impurities and break Z symmetry to some subsymmetry, does the order still exist in high temperature?
I'll just make a small technical comment. In this phase, the checkerboard phase, the original Z symmetry is broken to Z divided by 2. Or you can say 2Z. So the original lattice model has a symmetry of translations by any number of lattice, just translational symmetry. The checkerboard phase breaks the symmetry to translations by 2 units. So if you make a translation by 2 units, the picture doesn't change. And what it means is that the unbroken symmetry is still Z, but it's better to call it 2Z because it's translations by 2 units, and the broken symmetry is a Z2. Maybe that's what you said. I just didn't hear. So your question was if the symmetry is absolutely crucial to get something like that. I don't know. We did not think about it very systematically. I don't know how crucial it is.
Thank you.
Okay, is that a decent answer? Because I didn't hear the question fully.
Also, my basic question was, if I break the Z symmetry, this translation symmetry explicitly, my question was whether this order still persists in the high temperature.
But how would you define order? What will be the order parameter if you break the symmetry?
Right.
Maybe you want to break it to some subgroup.
Right.
Yeah, you could break the symmetry to some subgroup and see if you can still get some order at high temperatures, but I didn't think about it.
Thank you.
Yeah.
So there is one more question. So
if you look at the spectral functions of these quantities like psi at finite momenta, so do we have a non-trivial peak at finite momenta? And for example, for phi fields, is it that for small momenta it has a divergence, or is how do you define?
Are you talking about this
Second
model
part.
or the QFT model?
Yes, the QFT model.
Okay, so let me go to the QFT model. So what about phi?
If you look at the spectral function, the the Fourier transform.
Yes.
So how does it behave at small omega? Is it like it has an algebraic dependence, or?
How does the spectral function of phi behave at small omega?
Yeah.
At zero temperature?
Yeah, and of course at finite temperature.
At finite temperature?
Mentioning that there's an order, so.
But the order is in psi, not in phi.
Even in the psi also, is it that the 2-point functions have an algebraic dependence at omega equal to 0 or omega tending to 0?
I mean, I'll just say generally, I'm not sure about the particularities, but in general, because of the Goldstone bosons and symmetry breaking, you will see some behavior in the spectral density that is kind of beyond what you expect. Now, in this particular model, in the infinite line limit, you can just take n equals infinity. Even the phi field has a very interesting behavior. The spectral density of phi becomes very interesting and it becomes gapless. I kind of try to explain it here, but I don't have time to go into the details. At finite n, in this particular model, let's say n equals 50, I think phi 2-point function will be gapped. Well, up to the usual hydrodynamic tails. It's the psi 2-point function that has expectation value and maybe some exotic behavior.
And it is algebraic at small frequencies, or?
Okay, but in this model, it's not going to be quite algebraic because all you are doing is break ON times Z2 to ON. So the ferromagnet is due to a broken Z2. It's just a discrete symmetry, so it doesn't manifest itself in some interesting critical exponents.
Okay.
If you want like something more rich along the lines of what you're saying, you have to go maybe to 3+1 dimensions and break a continuous symmetry spontaneously at high temperatures. Like with a discrete symmetry, you won't quite see that in spectral densities.
Thanks.
okay, I do not see any other questions. So let's thank Zohar for today's talk.
Thank you so much for hosting me. Sorry I couldn't come in person.
Thank you very much for the talk, and give us.
By 5 p.m. I would know you have to go to this jury summons or not, and I'll send you an email.
Okay.
Thank you.
Thank you very much.